So in the last lecture, we had discussed with several examples the series and the parallel connection of resistances. Towards the end, we started talking about the series and the parallel combination of cells. So what we said is that when the cells are combined, like resistances, we can combine them in series or in parallel. We discussed the series combination last time, but let me quickly review this. So in series combination, as is common, the I remains the same. And the delta V, that is the voltage across, differs. So basically the circuit is very similar to the way you define a resistance series combination. So this is battery number 1. I already told you that we need to represent a battery by a combination like this. So this is an EMF source, and the resistance here is the internal resistance. So let us call it R1 and this is E1, and then I have a second one, and as is customary, I am combining or connecting the negative terminal of one with the positive terminal of the other, though if you were to connect it differently, then all that it will mean is you will have to subtract the voltages. So this is the second battery. So this is E2 and R2. And we said that we want to find out what is the equivalent combination. In other words, supposing you wanted to replace this combination with a single source of potential difference, and so this is, let us say, the point A, and this let us call it point B and point C. So between the points A and C, what should you combine? So this is A and this is the combination I am looking for, and of course there is an internal resistance. So I will again combine this and say this is E and let us say R, and this is the point C. So what we said is the principle is the same as we do in case of resistances, that is, start from any point. Let us suppose I start from the point C and go in the direction of current, supposing this is the direction of current. Later on today, when we discussed the general rule for finding out current, we will realize that it is immaterial what is your assumption regarding the direction of current, because if you have made a mistake in the beginning and your answer turns out to be with a minus sign, it simply means that the direction of current is opposite to what you have assumed to be true. So let us look at that. I start from the point C, go in the direction of current. This is the direction of the current. Now whenever you go in the direction of current, there is a potential drop when you cross a resistance. So drop, I will put a minus sign. So therefore what I have is Vc minus I times R2, and here I increase the potential because it is going from negative to the positive. So therefore my EMF has to be added here, so E2. So with this I have come to the point B. Then since this is a series connection, the current still continues to be the same, and the same current goes through R1, giving me a drop of minus IR1, and then again I add up another E1, and that by that I have come to the point A. So this tells me VA minus VC, that is the potential difference between the two ends of this section is E1 plus E2 minus I times R1 plus R2. So, if you look at this expression, it tells you that the equivalent EMF is given by E1 plus E2. So, this is E equivalent, and the equivalent internal resistance is simply given by R1 plus R2. So, that is Req. So, this is what actually you substitute this. So, let us write down that EEQ is equal to E1 plus E2 and Req is equal to R1 plus R2. Now, supposing I had instead of this combination, I had connected the polarities differently, and let us suppose I had this combination here. So, what we have is a situation like this. So, this is a seat of EMF E1 with internal resistance R1, and we connect this to another battery, but this time instead of connecting the negative terminal of one to the positive terminal of the other, we connect the two ends having the same polarity, and this is E2 with an internal resistance R2. So, let us give the same type of notation as we have been giving for the battery. So, this is seat of one EMF, and this is directed like this, and this is the seat of the other EMF where it is directed like that. So, let us look at what happens in this case. So, let me take this point as A and let me take this point as C. Now, we can assume the current to go in any direction we like. We have pointed this out several times. So, let us assume that the current is flowing from C and flowing out from the end A. So, in which case, if I start at C and come to the point A, what I have is Vc, which is the potential at the point C, minus, because I am traveling in the direction of the current, I times R2. Then I have a further drop because inside the battery I am going from positive terminal to the negative terminal. So, minus E2. Once again, when I enter the next seat of EMF, I have a minus I times R1, but this time I have a plus E1 because I am going from the negative terminal to the positive terminal, and I reach the point A. So, this is equal to V of A. So, this tells me that V of A minus V of C is equal to E1 minus E2 minus I times R1 plus R2. If you compare this with our previous expression, what we find is there is no difference other than the fact that there is a minus sign between E1 and E2. So, basically what we are trying to say is this, that the EMFs can be also treated as algebraic quantities, and depending upon the direction in which the current is moving in, if the current goes out from the negative terminal to the positive terminal, then of course this is EMF is positive, but on the other hand, if the reverse happens, then it is negative. Now the question is this combination that we have shown here is not really a preferred combination. You will find that in all appliances where you use serial combination of batteries, the terminals that would be connected would be negative terminal of one with the positive terminal of the other. The next question that we have is, why use a serial combination of cells at all? Why not simply use a cell which supplies a higher voltage? Now, the reason why I cannot do that is the following, that in addition to the voltage, there is another important quantity which characterizes a battery, and that is what is known as the capacity rating of a battery. So the capacity rating is essentially a measure of what is the life of a cell. And as we are all aware, that batteries work by the principle of chemical reaction. So whatever is the chemical reaction taking place there, supposing you have an electrolytic cell, so you have an electrolyte. Now what happens is this, that these ions which are, if you want to call them active ingredients, the positive ions go towards the negative terminal and the negative ions go towards the positive terminal, and they pick up or give away electrons, themselves now becoming uncharged. Now once they become uncharged, they become inactive and do not take part in further chemical reaction, and that would mean that the battery's life has come to an end. In the market, there is usually an assorted voltages and ratings available, and typical, for instance, is lead acid batteries, which supplies you 2 volts. The more common AA or AAA batteries, they supply you 1.5 volts. Nickel cadmium battery, which is another common battery available, gives you 1.2 volts. Lithium ion battery gives you 3.6 volts, and it's more convenient that instead of designing a battery with the specific voltage depending upon what your work requires, you pick up from the standard combinations that are available and design by using parallel and series combinations the voltages and the ratings that you want. So let us look at how to add cells in parallel. So the combination is very simple, that just the way you do resistances. So I have situation like this. So let us look at this combination. This is once again our same notation, E1 R1, E2 R2, and in this case, let us now notice here the most common combination in this is join the similar polarities end to the common point. This is the way the parallel combinations work. If you look up your remotes where parallel combinations of batteries are used, you will find that both of them say that put the positive terminal here. So the way it works is this. Supposing the current here is I1 and the current that is coming through that is I2. So this is your point A. Let's call this point B1. Let's call this point B2 and this point is C. and obviously since this is the negative terminal, current is coming like this and current is coming like this, and of course this is the way it is. Now suppose VB1 and VB2 are the voltages here and there. So my V is VB1 minus VB2, and look at what each one of them is. So this difference VB1 minus VB2, since it's a parallel combination, you can compute it either through this branch or through this branch, whichever you like. So that tells me that E1 minus I1 R1, I just go from the point B to this point. Since there is I am going in the direction of current, drop is I1 R1, I pick up EMF E1 and then come back to the point B, so that by that I get this difference. And this is also equal to, if I proceed like this, then this is also equal to E2 minus I2 R2. Now notice that the net current that I have got is this I here. Now this is clearly I1 plus I2. Now I will be talking more about this junction, what happens in a junction later today, but look at this, that I1 coming in here, I2 coming in there. The current is nothing but rate of change of charge. So therefore, if all the charges did not go out in the same time frame, there would be accumulation of charges. Now this is what is known as continuity. So by the continuity condition, I must have my current I is equal to I1 plus I2. And that I have seen is how much? I1, you can see if V is the potential difference there. So this tells me I1 is E1 minus V divided by R1, and I2 is E2 minus V divided by R2. I can rewrite it E1 by R1 plus E2 by R2 minus V into 1 over R1 plus 1 over R2. So look at this expression. Supposing I now find out what is my V, just rewrite this accordingly. So I get, firstly, I get a minus I into R1 R2 by R1 plus R2. This is simply multiplying both sides with the inverse of this, plus E1 R2 plus E2 R1 divided by R1 plus R2. Now look at this. Supposing I wanted to replace this by a single battery as before. So I have this, so this current is I, that's what is coming in. So notice that what I need to do is to have an equivalent. Notice that what would be my V? My V would be, supposing this is some R equivalent and this is some E equivalent. So I will have I times R equivalent as a drop. So minus I times R equivalent. So this term must stand for R equivalent. And this term here, so I must have plus EEQ. So I will have, this term is my EEQ. So therefore, now look at what I am getting. So my R equivalent is the same expression as what we got for the parallel combination of resistors. So therefore, let us write it down. We say the equivalent resistance that I have, R equivalent, is 1 over R1 R2 by R1 plus R2, which is the equivalent resistance of the two internal resistances. For R1 parallel to R2. Okay, let us look at the expression for EEQ a little more carefully. Now, this is E1 R2 plus E2 R1 divided by R1 plus R2. Let us do something. Supposing I write it like this, E1 R2 plus E2 R1 divided by R1 R2 and write it as R1 R2 divided by R1 plus R2. This is the same expression. I have simply put in the denominator R1 R2 there and R1 R2 there. Now, this expression here I can rewrite as E1 by R1 plus E2 by R2, and this is, as we have seen, is the equivalent resistance Req. So you notice that there is a very symmetric relation that we find for E equivalent, which is given by E equivalent by R equivalent is E1 by R1 plus E2 by R2. And if you had more than 2 batteries, of course you could still use this formula, that whatever is the equivalent resistance of all of them, and here the same type of a formula. We can do that. So basically what we do is this, that in case of a parallel combination, the arrangement is something like this. You see, typically a battery looks like this. This is plus. I am using the picture which is very commonly seen in normal 1.5 cell torchlight batteries. So this is the way we normally do connect these, and so this is my plus, and once again connect these, and this is my minus. So why parallel combination? So one of the things that you notice is this, the voltage that I get is the same because of the parallel combination, but it provides a higher capacity rating for the same voltage. So this is the way. So for instance, if you added two 1.2 volts batteries in parallel, and let us suppose each one of them has let us say rating of 1000 milliamp hours, because that the typical small batteries, they do not consume a lot. So what we get as a result is 1000 plus 1000, I get 2000 milliamp hours for the same voltage, and as a result, of course, you can calculate how much is the power difference. So let me now use these to work out a few example problems which will sort of tell you in what situation you can use this combination to your advantage. So let me start with this. Remember, I told you that normally parallel combinations are connected similarly. So let me give some voltages. This is 3 volt, this is 2 volts, and this is 1 volt. And let's say each one of them is 1 ohm simply. And this point is A. Let me take also the load to be 1 ohm for simplicity, trying to illustrate a point rather than actually work it out. So look at what I have said. What I have said is this, that this parallel combination I can replace by a single battery. And how much would that be? So the equivalent resistance here is simply the parallel combination of 3 1 ohms, which of course will give you 1 by 3 ohms. And the equivalent voltage, EMF, is given by this formula, EEQ by REQ equal to E1 by R1 plus E2 by R2 plus E3 by R3. Now E1, R1, R2 and R3 are the same and each equal to 1. So this is nothing but just sum of the 3 voltages, which is 6 volts. So that tells me EEQ is 6 into 1 by 3, which is equal to 2 volts. So what we are saying is this, that this combination you can replace with a single battery of 2 volts having an internal resistance which is 1/3 of what each one of them had. So, but if this is all that is there in a circuit, then of course the combination of batteries is not supplying any current. The circuit is open. So if it is not supplying any current, supposing this is my I1, this is my I2, and this is I3, and this is of course, as we have seen, is I. And what we are saying is this is 0, no current. Now we can actually check how does it work. See, the way to do it is the following, that suppose I come from here to there. So we have already worked out the potential difference between A and B is 2 volts. And so therefore if I start from here, go along this path, then I notice that I start from 3 volts minus 1 into I1. So my equation is 3 minus 1 ohm into I1. That must be equal to the potential difference between these two, which is, because there is no current, it is the same as 2 volts. Which tells me that I1 is simply 1 ampere. Let's look at, supposing I went like this, because this is a parallel combination. I can go any way I like. So I pick up 2 volts minus I2 into 1. So 2 minus 1 into I2, that's equal to 2. So that gives me I2 equal to 0. If you did the same thing by the third branch, you will find I3 equal to minus 1 ampere. That is, the direction I have shown is opposite to what actually takes place. Now, let me ask a slightly different question. Suppose in this, somehow I shorted the central resistance, that is the internal resistance, if somehow or other I could short it. So, what is meant by shorting? Shorting simply means that the two ends of the resistance that you have got, you are going to connect them by a wire of no resistance at all. So let me draw that picture again. Okay, so basically what we have said is the following, that supposing you did this, so that this resistance is effectively removed from circuit. And not only that, till now I discussed about a circuit which was open, but let me also connect A to B. There is a resistance here, which is 1 ohm resistance. That is your load resistance. And this was 3, this was 2, this was 1, and this was, each one of them was 1. This is not really material anymore. So let us look at what does one do for such a problem. So firstly, this is almost an introduction to what I will be later on discussing as the loop law, but I do not need it right now, because that is the way I have been discussing, that is, I can go around any path as long as I remember the following. If I climb up a potential, I add that amount of potential in a battery. If I am traveling in the direction of current, there will be a potential drop of I times R if the current through the resistor is I. So let us look at what I can talk about. Now notice one thing. So let me do the following. Suppose I decide to travel along this path. What I am doing is the following, that remember that our currents were I1, I2, I3, and this current here was I. Earlier it was 0, but now because I have provided a path for the current, so this is I, this is equal to I1 plus I2 plus I3. Now look at what would happen if I took this path, A, go to B, go to C, go on the top line, come back to D and come back to A. That is a loop. We will be discussing about loops as we go along. But look at what am I doing. So firstly, since this is I1, I pick up an E1. So E1 minus I1 R1, R1 is 1 into 1, minus I, which is I1 plus I2 plus I3 times 1, of course, that is equal to 0, because I have simply returned back to the same point. So this gives me, since my E1 is 3, so I get 3 is equal to 2Y1 plus I2 plus I3. So that is my equation number 1. So within this loop, for example. So here again what we will do is this, I have a I1 into 1, and then I travel through this red section, there is no resistance, and pick up the voltage 2, but this time it is subtracted because I am going from positive to negative, and then return back there. So that will give me an equation like this, that I1, because that immediately solves for I1. So I get I1, see there is an I2 there, but it is not coming into the picture in this loop when I go along, because the resistance is not there. So I get I1 equal to E1 minus E2, which is equal to 3 minus 2, which is equal to 1. So that immediately gives me the solution, I1 is equal to 1 ampere. Now you could do the same thing for instance, for any of these loops. You can do for this loop and show that I3 is equal to minus 1 ampere and I2 is equal to 2 amperes. Let me take another example. Supposing I have a simpler battery system, RL equal to 2 ohms, and let us take them to be the usual 1.2 volt batteries. This is 0.15 ohms, this is 0.15 ohms. Now, I first find out what is equivalent resistance. So, that is simply 0.15 parallel to 0.15, so it is 0.075 ohms. And E equivalent divided by this Req, which is 0.075, is equal to 1.2 divided by 0.15 twice. So, it is 2 into 1.2 divided by 0.15. So, this is equivalent to a battery EEQ which has the same voltage, namely 1.2 volts. Now, this is purely because of symmetry, that is the two internal resistances are the same. Now, you could verify that this indeed is true by realizing that supposing this is I1 and this is I2. Now, by symmetry I1 and I2 must be the same, because this battery combination and this battery combination is identical. So, therefore, what I get here is a current which is 2I1, because I1 is equal to I2. So, let me look at any one of the loops come like this, go along any branch. So, if you look at the Kirchhoffs law for this situation, you find that minus 2I1 times 2 ohms minus I1 times 0.15 plus 1.2 equal to 0. Now, which gives I1 into, I will not be doing the algebraic addition for a particular reason. So, let us write it as 4 plus 0.15 equal to 1.2, which gives the current I1 to be 1.2 divided by 4 plus 0.15 amperes approx. Now, the actual current in the circuit is I1, that is equal to 2.4 divided by 4 plus 0.15, which you can rewrite as 1.2 divided by 2 plus 0.075 amperes. This 2I1 is the current that is passing through the 2 ohm resistance. So, notice that this 1.2 ampere, that 1.2 volts that we have written down, that is the equivalent EMF of the parallel combination of the cells. As you know that two equal valued EMFs give the same EMF when they are put in parallel, and this denominator is the serial combination of two plus the equivalent resistance of the internal resistances of the battery. With this, let me give an introduction to the most celebrated law of current electricity, which is known as Kirchhoffs law. We have seen lots of examples of situations where I can simplify the systems or circuits by looking at the series or parallel combination. In today's and the next lecture, we will be giving several examples of circuits which are too complicated to be broken into such simple combinations which are either series or parallel. So, what we will do is this: we will try to get a method of how to solve for such circuits, and So these are done in a very systematic way by a set of two laws. So these are known as the Kirchhoffs law. But before I discuss what is Kirchhoffs law, let me define, but let me first put one circuit just as an illustration of what I am talking about. This is a circuit which you can solve by other methods, but I am just using it for the purpose of illustration so that you can see what is actually happening there. So let us call these number these points 1, 2, 3, 4, 5, 6. Now first I define a branch point or a junction. What is meant by a junction? So junction is a point in the circuit wherever 3 or more branches or 3 or more conductors join. Whether there is resistance in it or just a resistance-less wire, it does not matter. So a junction is a point in the circuit where 3 or more conductors are joined together. In this example, we have several junctions. For example, this is a junction A. You can see it. This is one conductor, this is one conductor, this is one conductor. As I told you, it is totally immaterial whether the conductors that are coming in have resistances or not. So A is a junction. This point B is a junction. This and that. C is a junction. D is a junction. So these are what are called as junction. Then I define what is called a loop. Loop is much simpler, as the name suggests. Any closed path in the circuit is called a loop. So in this circuit, which let me redraw. So our numberings were 1, 2, 3, 4. I had A here, B there, C there, D there, and let's call these numbers 5, 6. Now there are many loops. So for instance, if you look at this left hand side small square like loop, 1, 4, C, B, 1 is a loop. So is B2, 3, C, B. I'm showing loops which we are traversing in different directions, sometimes clockwise, sometimes anti-clockwise. Then, for example, 1, 2, 3, 4, 1 is also a loop. This 1, 2, 3, 4, 1. There are many which are not immediately visible as a loop, but they are also loop. Start, for example, from 1. So 1 to A, traveling on the outside 5, 6, B, 2, B, 1. So 1, A, 5, 6, D, 2, D, 1 is a loop. There are others. There are A, 5, 6, D is a loop. Sorry, A, 5, 6, B, then you can come down 3, C, 4, A is a loop. So these are various examples of loops that are there in this. There are two laws. First law is called the junction. So this is Kirchhoffs law. The first law is called the junction rule. The junction rule says that the algebraic sum of currents flowing towards a junction is 0. So let me write it down, then I will illustrate what it means. Algebraic sum of currents arriving at a junction is 0. So this is also, you could have stated it in a different way. You could have said algebraic sum of currents leaving a junction is 0. I will explain what it means. So let me first write down this sum over I equal to 0. So supposing there is a junction where my currents arrive like this. So let me just give some name: I1, I2, I3, I4, I5. Now I use the word algebraic. It's not just I1 plus I2 plus I3 plus I4 plus I5 equal to 0. I have to check, is it going towards the junction or it is going away from the junction. Supposing I decide that the current arriving at a junction is positive, then my I1 is positive, I3 is positive, I4 is positive. But this is negative because it is leaving a junction. This is negative because it is leaving a junction. So this is what is meant by algebraic sum. If I1, I2, I3, I4 and I5 are just the magnitudes of the current with a direction as shown here, then you know that for if I1, I2, I3 etc. are just magnitudes, with directions as shown, then it tells me that I1 plus I3 plus I4, which are coming in, so hence positive, minus I2 minus I5 equal to 0. This is what is meant by algebraic sum being equal to 0. Remember, right in the first lecture we pointed out, a current is not a vector. This is not the way the vectors add. Vectors add by specific rules, parallelogram rules between two. So this illustrates why we had made a statement that currents are not vectors. We have seen current densities are vectors. Okay, so that is junction rule. Simple rule, just take care of the direction of the current, then you can write down the first rule. Next rule is called loop rule. This says in any loop, any closed loop, the sum of voltage difference is 0. That is sum over I, Vi equal to 0. Remember, we have been talking about this for a very long time. So What is junction rule? Junction rule is a mere statement of continuity of charge flow, because at any junction, whatever charge is coming out, because there is no accumulation, they have to go out, and hence the word algebraic sum is 0. Now, the loop rule arises because for static fields we have seen that integral E dot dl is 0, and we have been talking about this, that suppose I have a resistance. So, this end is positive, this end is negative. Now, this is in the sense that if the current is flowing like this from so the direction in which the current is flowing is such that the positive end is connected to the positive terminal of the battery. So, therefore, this is the way the current is going. So, higher potential of the resistance is the point where the current enters. And of course, we normally talk about a ohmic conductor. So, delta V, that is the potential drop, this is equal to I times R, and that drop has to be taken care of as you go around a loop. Now, in the seat of EMF, delta V is greater than 0 if we are going from the negative terminal to the positive. You recall that we have been having this type of a notation for our battery, and this is the norm that we had. So, what we are saying is this, that in using Kirchhoffs law, if you are traveling like this, in this way, then your delta V turns out to be positive. And the reverse would be true, that is, if you are traveling in the reverse direction, if from positive to negative. So, let me put it in the same picture. So, this is greater than 0. If on the other hand we are describing it like this, then this delta V is less than. Now, you do not have to know a priori what is the direction in which the current is flowing. You are allowed to use make any assumption regarding its direction, and at the end of the calculation, if the numbers turn out to be negative, then you know that your original assumption was wrong and the direction of current should have been opposite to what you have assumed. So, let me return back to this example that I gave you earlier. So, let me look at a picture like this. I will do numerical problems next time, but at this moment let me illustrate how it is going. Consider a circuit like this. So, let me number them. This is R1, this is R2, let us call this R3, let us call this R4. Now this says R4, let us just call this load resistance as R, this is R5. So how do I look at this? How many unknowns are there? Let us look at this first. So there is this general current which is going out, let us call this I. Now this I gets divided at the junction. Remember I said that the algebraic sum at this point is 0. So I is coming in, but supposing you assume that I1 and I2 are going out. This immediately tells me that if I1, I2 and I3 are assumed magnitudes of the current, then I1 plus I2 must be equal to I. And keeping that in mind, supposing we say this is I5, this is let us say I3, this is I4. Now look at how many unknowns are there. I got I, I1, I2, I3, I4 and I5. 6 unknowns are there. I need to get equations corresponding to that. Generally, I should be looking for 3 branch equations and 3 loop equations. Now, if in principle, if you blindly do things, you will get many more equations. Because as I have told you, there are many ways you can count the loops. Junctions are fixed, because I need to simply see whether there are 3 points or not. For example, here I have a junction here, I have a junction here, I have a junction here, I have a junction here. Already 4 junctions are there. This is a loop, this is a loop, this is a loop, but loops there are too many. So when I try to solve this problem, if I blindly write down the number of equations, these equations will be many more than the number of unknowns that I have. That makes many of these equations are not independent. So one has to be careful in choosing which equations you write down. What I will do next is to take several examples of circuits and solve them using these 2 sets of 2 rules which are known as the Kirchhoffs laws.